So there's a massive pumpkin. Oh, it's so cool. Yeah, it's so cool just jumping to exactly the right ones. Oh man, yeah. Harvest. 700. Ah, that's very efficient, isn't it? That's pretty satisfying. Welcome back to the farm I was replaced. Today we're going to double the size of our farm and incorporate pumpkins into our system. So if you want to find out how, stick around. So let's figure out how pumpkins actually work in this game. We can unlock pumpkins right away. Pumpkins grow like carrots on tilled soil. Okay. They require pumpkin seeds to be planted, which cost 1 carrot each. When all the pumpkins in a field are fully grown, they grow together to form a giant pumpkin. The yield of a giant pumpkin is the cubed side length of the pumpkin. Okay, so cubed is pretty enormous. So yeah, like you can see here, a 4x4x4, 4x4 pumpkin. Oh, okay, so it's like the squared size, but the cubed number of resources. Interesting. So it's actually not as impressive as it sounds. Like you hear cubed and you think, wow, that's massive. But in reality, it's like order x to the 3/2, which is the square root cubed. So it's not that big of a deal. Obviously, all else being equal, we're going to want to grow large squares of pumpkins because that's better. So it's not like we want single pumpkins dotted around all over the place, but we might still deliberately decide to do smaller squares if we've got other priorities at the time. The problem is about 1 in 5 pumpkins will die before they grow up. A pumpkin that dies will simply disappear, so you can plant a new one. Interesting. I wonder if they die after they grow up, because that seems really important. So we'll have to experiment with that because the documentation doesn't tell us. And it presents some interesting challenges for our system because our system works on a cell by cell level at the moment. And this is naturally an entire grid sort of decision that we've got to make. We've got to decide, well, is it? I don't know, like maybe you just get lucky and get a large one. I don't know, we're going to have to experiment and see how this goes. But before we do that, you guys had some interesting comments that I want to address quickly around wood. So a lot of you mentioned that actually if you look at the documentation for trees, it's not any adjacent cell, it's only cells adjacent to the north, east, west or south. So actually diagonally adjacent doesn't count. So we can amend our modulo logic here to be something more like x plus y modulo 2. And you probably don't need the brackets here, but I just like to put them in to be clear. It depends in this language whether modulo binds more tightly than plus, but it's always better to be safe than sorry and just throw the brackets in. So this is going to plant our wood on a checkerboard pattern, which is obviously more efficient than the method that we were using before. So that's great. The other thing that you guys mentioned was if we're really short on wood, say we've got like 0 wood and we really want to catch up, then we can still plant bushes in the spaces between. At this point, I'm also going to move this logic to below the carrots because I only want to do this sort of faffing if we're really sure that wood's a problem for us. So firstly, we decide, okay, wood is our target resource. And then we decide, are we allowed to plant a tree on this cell? And if we are allowed to plant a tree, then we say the best resource is an entity's tree. And if we're not allowed to plant a tree, then we say that the best resource is an entity's bush. So in this case, if we're super short on wood, then we're going to plant trees in this checkerboard pattern and then plant bushes on the cells in between. So let's try and get ourselves into a situation where we would be really short on wood. Okay, so we can upgrade our carrots. Now we're really short on wood and we're running this. This time we're planting the trees in a checkerboard pattern and then bushes in between. So that's working perfectly. And we'll leave that running to try and catch ourselves up on wood. Before we dive into pumpkins, I just want to have a peek at our unlocks, see what we're able to unlock. It seems like the only thing we can get right now is multi-trade and sunflowers, and I think it's going to be helpful for us just to take a peek at how sunflowers work. So we can bear that in mind while we're working on pumpkins so we don't get ourselves down a rabbit hole that will not be extensible to sunflowers. So let's unlock sunflowers and also multi-trade. Buying items just one by one takes a lot of time. You can now specify the number of things. Okay, so we can easily extend our purchase up to utility to use the new multi-trade. So purchase up to, while num items is less than quantity, this now becomes if num items is less than quantity, then we trade for quantity minus num items. I wonder what this does actually if we can't buy enough. Does it buy... If the item cannot be... Let's have a look. Because our previous solution just did a partial order. If you can't afford that many, this will simply do nothing. Ah, that's worse. Yeah, screw that. Let's stick with what we were doing before. I liked our method before. We do a partial order rather than a completely failed order. So, veterans of the game will probably tell me, by the way, that I'm calling too many functions. The goal here is not to... We're on phase 1. Phase 1... The goal is to build the most versatile farm that incorporates all of the entities. Later phases, we're going to worry about optimization a little bit, but really here, we're all about building a versatile system that's easily extensible to new entities and doing that in such a way that we can learn something about Python in the process. So we're not talking about god tier performance at this point. We'll get to that later. Right now, it's all about the versatility. So we also unlocked sunflowers. So let's have a look and see how sunflowers work. Sunflowers collect the power from the sun. Harvesting them will give you items power equal to the square root of... There are so many square roots and cubes and stuff in this game. I love it. Harvesting them will give you items power equal to the square root of the number of sunflowers in the farm. If you harvest a sunflower that doesn't have the maximum number of petals, all the sunflowers will die. Damn. Base growth time between 4 and 6 seconds can grow on soil. What the hell is an item's power? What does a power do? Power. Obtained by harvesting sunflowers, the drone automatically uses this to... Oh, okay. So I think it's time to have a real think about pumpkins. Let's just see what happens if we throw it into the framework. Let's see how our framework can cope with this sort of stuff. So we need to do some more specialism. Pumpkins have seeds as well. So if the entity is a carrot, then we do a carrot seed. Otherwise, if the entity is a pumpkin, then it's a pumpkin seed. Pumpkin seed. Okay, and the grand type is also going to be tilled soil like carrots. So if the entity is carrots or the entity is pumpkin. So we've got the grand type, the seed type. Everything else should work as is in utilities. We don't need to worry about that. Now we just need to make the decision to plant it. So again, we don't yet have lists, right? Lists actually cost us pumpkins. So we're going to have to extend this without lists. So let's go ahead and do that. So pumpkin count is how many pumpkins that we have. And then it's going to work exactly the same as carrots. So carrot count, if instead of being carrot count now, this is all going to be pumpkin count. So if the pumpkin count is less than the best count, which it is going to be for quite a while, then we want to select pumpkins as the resource. So this is going to tell us something about how pumpkins work. Right now, obviously, because we're completely devoid of pumpkins, we're going to be planting pumpkins on the entire grid. Let's see. Okay, so we're planting pumpkins everywhere. So that's all working. They're becoming... we're harvesting too quickly to learn anything, really. Obviously, this is going to work. This is going to give us a bunch of pumpkins. And it have this kind of nice natural property that when we're really short on pumpkins, we plant more pumpkins. So by random chance, they just have more of an opportunity to get big. In reality, especially since we built this checkerboard pattern out of wood, by the time we get even, we're only ever going to be getting single pumpkins because the pumpkins just would not have the opportunity to grow past the trees. So let's clear the farm. Let's get back to a blank slate and let's plant a full set of pumpkins and see what happens. So they're dying, as you can see. 1 in 5 dying, apparently. So we're noticing a few things. So yeah, so this looks stable, right? So we can assume that they're only going to die on the way. So that's interesting. We've identified a pretty major problem with this can harvest in that for pumpkins, maybe we don't want to harvest right away. Maybe we want to move on. But you know what? This is going to get us a bunch of pumpkins. And it would allow us to expand the farm. Like, we could expand the farm really quickly here. I'm almost inclined to just, like, let's learn more. What the hell is a treasure chest? You can't grow a treasure chest. I'm inclined to just run this and just see what happens. Like, where do we get? If can harvest. Why is this doing nothing? Why is this doing nothing? I must be missing something really obvious. Oh! Oh! Okay, so we... Right, so this logic needs to be different. It's not just can... Yeah, I was being stupid. It's not just can harvest. It's if the entity type is none. Okay, yeah, right. So if can harvest or get entity type is none. I guess we only want to harvest as technically if we can, but... this will work. Okay, so let's see what this is doing. This is going to get some pumpkins. If we're fortunate, they get big. I do feel like we should try and take advantage of the big ones. A lot of the time when we're getting lucky with them, we're just not being patient enough. The thing is, this is working. Let's expand the farm and see what happens. Yeah, so that was cool. So because we expanded the farm, we're now much slower in getting back to the origin. So we're giving the pumpkins more of an opportunity to join together, which is very nice. Huh, Sometimes the pumpkins are missing their little green knob. I'm honestly inclined to just leave this as is. It's really demonstrating the power of some of the things we've built up here, because it just worked out of the box. All we had to do was add the seed type for pumpkins and the ground type, and then prioritize pumpkins accordingly, and we were off to the races with them. Let's keep expanding. And I think we need speed as well to see what we're working with here. So we're short on carrots and pumpkins, so we're planting carrots and pumpkins. This is just working. Obviously we're wasting a lot of time because the entire grid's grown here, so this isn't a case where watering would be useful, it's a case where sunflowers would be useful. I really want to see what happens when we get back up to equal. We're still getting massive pumpkins. Oh, the knob's in the wrong place. So pumpkins are already just giving us more stuff. And given what I said right at the beginning about the fact that because it's only order x to the 3/2 rather than actually cubed, it's not actually that important to make them huge. Yeah, I'm going to let us get ourselves up to even, and then we'll see what the damage looks like at that point, because I think maybe wood is going to throw a spanner in the works. Okay, so we still grew a big pumpkin, a couple of big pumpkins. I almost want to get some maths out and just say, like, given that the probability of a dead pumpkin is 1/5, how important is it really to try and grow the big ones? Because there's one thing, there's like making the space to grow big ones, but then there's ensuring that the big one actually grows, like going back to tend to the cells that need pumpkins. I don't know, we're growing pumpkins, everything's working. Let's get some upgrades. We can get some speed, sunflowers, utilities, lists, obviously great. Dictionaries, fertilizer. We'll get this just to unlock mazes and just have a look at what's in store for us, because I've heard that mazes are incredibly difficult, so we're going to have to learn about those. And mazes are obviously gating a lot of the end game stuff like cactus and dinosaurs, and even dictionaries. So wow, they're not optional at all. So yes, fertilizer. Waiting for plants to grow is just not efficient enough anymore. Well, we're going to need more sunflowers and more speed before that is the problem for us, because currently the plants are growing way faster than we can deal with. Fertilizing can make plants grow instantly. I do wonder if when we're really deficient on pumpkins, it would be better to just go into pumpkin mode and allow the entire grid to be a pumpkin. Is that better? Let's see what it looks like. We can eyeball it. We really need benchmark to tell us whether it's better, because I assume this'll give us like a pumpkins per second sort of metric or something. Let's just see how efficient waiting for pumpkins would be. So we want to traverse the farm and do plant in cell, which is this, but we want to override entity to plant to be always pumpkin for now. So entities pumpkin. So traverse farm with plant in cell. So let's run that. That's going to plant pumpkins everywhere. And now we are going to want to traverse the farm, and if the entity type is none, we're going to plant the pumpkin again. So let's do that until we've got a bunch of pumpkins. Let's just see how efficient this is going to be. Okay, so there's a massive pumpkin. And then if we harvest this, harvest 700. Ah, that's very efficient, isn't it? That's pretty satisfying. Huh. There is definitely a trade-off though, because like a 6x6 pumpkin has 36 opportunities to fail, whereas a 3x3 or a 4x4 has fewer opportunities to fail. You have to think about this. We're wasting a lot of time now where the plants are fully grown, but the drone isn't fast enough to harvest them. So I think we're going to have to remember how sunflowers work. Sunflowers collect the power of the sun. You can harvest that power. Only one of the sunflowers with the most petals can handle this. If you harvest a sunflower that doesn't have the most petals of all of the sunflowers on the farm, the power will destroy all the sunflowers on the farm. Measure returns the number of petals in the sunflower under the drone. Sunflowers have at least 7 and at most 15. They can be measured before they are fully grown. As long as you have the power, the drones will use it to run twice as fast. I'm kind of curious about experimenting with how much faster this is actually going to make us. and how many sunflowers we need to power the drone. So let's extend our framework to handle sunflowers. So if the entity is a sunflower, then we're going to need a sunflower seed. We need tilled soil, in which case I'm just going to make everything go in tilled soil except for grass. Okay, so now we can plant sunflowers if we choose to plant sunflowers. So for now, let's just plant sunflowers in the bottom left corner. If we've only got one sunflower, then we don't need to worry about measuring them or anything. I'm just curious how much power we harvest and how much faster that makes the drone. So if X is 0 and Y is 0, then we're going to just bail out early and plant a sunflower. In fact, we could do this right at the top. We don't need to check any items in that case. Okay, so this is going to plant us one sunflower down here. Takes quite a while to grow. Okay, it used up the power quite quickly, like one row basically. But it does go a lot faster. Sunflowers seem really worth it. Nice, okay. Yeah, it's so dissatisfying, isn't it, that the entire grid here wants to be harvested, but our drone just isn't quick enough for it. Alright, so that gives us a target to aim for. When we begin traversing the farm, we want to be positive on power. And we want to be positive for forever. And if we're not positive, then we want to plant more sunflowers. We need to keep track of which sunflowers is the best to decide whether or not we can harvest it yet. And we're only able to do that right at the end of the traversal. Interesting. So let's see, how would sunflowers work then? We can plant them using this logic here. So like if num items power is, let's say, let's have a target of 1. I don't know if that's the right number. Maybe it needs to be something else. Then we're going to plant some sunflower. I mean, this is just going to fill the entire grid with sunflower for now. So what was the deal? So the square root of the number of sunflowers. So if there's 1, you get 1 power. If there's 2, you get 1.4 power. Now we need to harvest the best sunflower. We can worry about how to integrate this with Traverse Farm in a second. So move to origin, and then let's have best. Let's do best sunflower petals and best sunflower position. And that's going to start out being none, I suppose. None and 0. So move to origin. If we're on a sunflower, if we're on an entity type that's a sunflower, then we can get the number of petals by calling measure. So this position petals equals measure. If this position petals is greater than the best sunflower petals. I'm thinking if we hit a 15 we can bail out early, but for now let's just keep plowing on here. So best sunflower petals equals this position petals, and then best sunflower position is get pos x, get pos y. So I'm making a tuple out of these, hopefully, we'll see. And then we want to move to, no, we don't have like a move to yet. We only have move to origin, we don't have move to a specific position. That seems like it'd be useful. For now, let's just print it out and we'll go harvest it manually and just see what happens. Zero, 3. So we want to move to, we're in 0, 0, so we want to move upwards, Y. So we want to move north a few times. And then this should be 0, 3. Zero, 3. Cool. Okay, so let's harvest here. How much power do we get? We should get 6 power, right? We get 6 power. Oh, and that only harvests the 1 sunflower. Interesting. I kind of wondered if it would just harvest everything, a bit like the pumpkins work. Did it tell me that? As long as you have... Oh, yeah, it said, yeah, if you harvest the wrong one, then it clears everything. But if you harvest the correct one, then you're good. Okay, so maybe planting the entire grid isn't so bad, because that'll give us 6. And then we could go to the next one and get another 6. As long as we could keep track of this appropriately. Oh, yeah, we could... Let's try this. See how much power it gives us. It should give us a ton. And then we'll find out how many full farm traversals we can do like this. And I think we can incorporate this into our plan. Nice. I can see how this is going to work. So we have lists, which is great. We do not yet have dictionaries, so we're going to have to do this with lists. We're going to do nested lists. So we're going to have a list of lists, and the first index into that is going to tell us how many petals we have, and the second index into that is going to tell us the positions there. So let's create ourselves a new utility for getPos as a tuple, because I think that's going to be something that we're going to want. So getPos is going to return the tuple getPos x, getPos y. And now we're back in here. So we're going to have sunflower petals is going to be a list of lists. So let's say that we only had petals of 1 and 2. Then we might have a list here that's like none, and then say there's a sunflower at position 2, 3 that has 1 petal, a sunflower at position 4, 5 that has 1 petal, and then a sunflower at 3, 3. A sunflower at 3, 3 that has 2 petals. This is the sort of structure that we're going to look at. And then we're going to go through and harvest them in order. So we'll harvest this, and then we'll harvest all of these. And then we'll have harvested an entire grid, and we can go back to planting as normal after that. Right, that's going to require a few things. Obviously, we can build up this structure using basically the same logic that we've got here. I don't want to have to traverse the list and see if this is the... So we need to build up this structure first. So this position petals equals measure. And then instead of just doing this if stuff, we're going to say sunflower petals. Okay, so let's have a create list length method. So list, I probably don't want to call it list. It's going to be like new list is that, and while length of the new list, let's have a 2D list, create 2D list. While the length of the new list is less than the length, then new list append like that. And yeah, like I say, we go 7 to 15. I think we're just going to want to offset everything by 7. So we'll start, instead of having this none here in our example from before, we'd just say that 1 petal corresponds to the 0th index. So this is going to give us a 2D list, and we're going to have a length of 8. So we should really have some constants here. So it's like min sunflower petals 7. And actually, when I'm doing constants like this, I like to put the bits that don't change right at the beginning. So sunflower petals min is going to be 7, and then sunflower petals max is going to be 15. So our 2D list is going to be of length min minus of length max minus min. So sunflower petals equals create 2D list of sunflower petals max minus sunflower petals min. And that's going to just help us out a little bit in case the game's patched or there's some sort of upgrade that changes the number of petals. So this should give us our new sunflower petals list. So let's just check. We've got our print debug now, so it seems like a good opportunity to use it. So this creates this. Yeah, we've not actually implemented anything down here yet. So I would really like to use traverse farm, by the way, which means I want to make this stateful. So we'll probably come back and refactor that in a sec. Let's actually finish this off and see. So sunflower petals of this position petals minus the min. So sunflower petals min is going to get a new element, which is this position. Let's see. So we start with... we need to actually return the new list, of course. So we start with that. Then we go through everything and we want to print. That was really fast, actually, so I'm not too worried about traversing the grid multiple times for this. I don't want to use too much power generating the power, though. That's the thing. Okay, so we start with the empty 2D list, and then now we've got a long old list, and it tells us all the positions. So that seems to be working right. Now what we need to do is go through this list in reverse and harvest those specific things. And that does make me think like it'd be really nice to have a move to specific position function. Let's create a move to function. That seems like it's going to be useful in general. So instead of move to origin, well, as well as move to origin, we're going to have move to xy, which I guess we're going to want to overload. This is the one that's going to be easier to implement, but for us calling it, we're going to want move to with a position tuple. And that's going to call move to position tuple 0, position tuple 1. Okay, so now we need to actually implement this move to thing. It's going to work pretty similarly to this. We're still going to have this potential, like it'd be easier to move to the other side of the world. So while our X position is not correct, then we're going to want to move. But which direction do we move in? That depends. That depends whether we're to the left or to the right. And it's a lot more complicated than from the origin, because it's not just get world size over 2. It's about the absolute difference. In fact, we can do this, just do this once, right? Because like these two branches have exactly the same thing. Let's say move on axis, and then we'll do the x-axis. So target x is going to be x, and then we'll say, okay, how does our axis work? Well, it has a position function, which looks like that one, and it has a coordinate system of east, west, and then we're going to have move on axis y, get pos y, and the coordinate system for y works like north, south instead. Now we only have to worry about axes. We don't have to worry about moving, we don't have to worry about duplicating this stuff. So we're gradually breaking the problem down, making it a little simpler for us to worry about. Move on axis, and we're going to have a target. So we're only thinking one-dimensionally now. We've got a position function in, so east or north increases your coordinates. So this is going to be like our increase direction. And west or south decreases. So this is going to be like our decrease direction. Right, okay. So we can do the old version that's not taking advantage of wrapping around the grid quite easily now. We've got our target, so while our get, instead of get pos x, it's going to be while our position function, which we need to call, is less than the target, say, then we want to move in the increase direction. And then while our position function is greater than the target, we want to move in the decrease direction. So this works. It's not the exact most efficient way of doing it. So let's try it. Let's check that it works, and then let's go back and implement the efficiency of wrapping around the grid. Move to 4, 2, which we expect to be here. No, error. Move to takes 1 argument. Oh, interesting. So you can't do this. That's a shame. In Python, can you overload functions? I've been thinking about Java recently. I don't know, can you overload functions in Python? Probably not, actually. In Python, you just have optional arguments. Oh, yes, you can do defaults. Okay, so we can do the desired behavior here by doing X or position tuple, and then making Y optional. So if you pass in X and Y, then this is an X and this is a Y. Otherwise, this is a tuple. So let's say if Y is none, which is going to be equals none in this language, then X is going to be equal to X or position tuple. X or position tuple 0, Y is going to be equal to X or position tuple 1. Else, we have a Y, which means we just need an X, and that's going to be the value of this thing. So we're going to call this function by either passing in coordinates or the tuple that we've just created. And now down here we call this with X or Y. I'm sorry about that, I had a complete brain fart about how overloading works in Python. Of course this is how it works. So let's try moving to 4.2. That worked. Let's move to 2.2. Nice. Let's move to 0.2. But now here's the problem. If we want to move to 5.2, which is the cell right here on the other side, we're going to move the long way around rather than moving the short way around. And we want to move the short way around. So let's try and figure this out. Again, we're only thinking on one axis, which is really nice. We basically need to decide which direction to go into. And then while our position is not equal to the target, then we'll move into in that direction. So in fact, we can make all this work by ignoring decrease just for demonstration purposes. Let's say the direction is always going to be increase. Then while the position function is not equal to the target, then we can always move in that direction. And this will still work. It'll still get us there, but we're just always going to be moving up and to the right. So here, if we want to move to 2.2, we go off the right-hand side of the grid rather than going directly there. But it can still traverse us to any position on the grid, which is pretty interesting. I just realized, by the way, that I didn't show the tuple stuff working either. If I want to move to something with a tuple, then I can pass in the tuple and that's still going to work. So that moves us to 0.4. Now we need to intelligently decide which direction to go into. So rather than increasing always, we got to decide to increase or decrease depending on the difference between their coordinates. Let's say current position, which is going to be the position function, and then the target. So increase steps is going to be the target minus the current position. So say we wanted to move to coordinate 7 and our current position is 2, that's going to take 5 steps. The problem with this occurs if the target was 1 and our current position is 2. Then this is going to give us an answer of -1. But actually we're not taking -1 steps, we're taking the full grid size -1 steps. So we need to modulo this by the world size. So let's try this, modulo world size. So that's the number of steps to go in the increase direction, and then the number of steps in the decrease direction is going to be decrease steps, which is exactly the same stuff, except we're going in the opposite direction. So by default, let's move in the direction of increase. If decrease steps is less than increase steps, then we're going to move in the direction of decrease. So let's test this out. So here we're at 0.4, so let's try moving to 5.4. We should move left, which I think we did. If we move 4.4, then we should move left. 3.4 should move left. 2.4 should move left. 1.4 should move left. Okay, so we're moving left. That's good. And then if we want to move to 1, 2, 3, 4, say, then that's close enough that we should be moving right, which we did. Okay, this move 2 seems to be working. I only tested it in one direction, but that's okay, because if it works in the X direction, it definitely works in the Y direction. So now we have a way of moving to specific cells on the grid. We can replace our move to origin function with just move to 0, 0. I think it's still kind of nice to have move to origin. How many times is it called? That's the real question. Move to origin is called there. Is that the only place? Okay, it's only called there. That means we don't need the function anymore. We've got move to, which is super efficient. So move to 0, 0. And this is where having those like fake overloads is really useful, because when I'm writing the code, I want to just write 0, 0. But when I'm building these things out of sunflowers and I'm going to be calling getPos, I want to be passing in the tuples. So to recap on where we're at, we've got this move to function now. We've also got our full sunflower petals 2D list, which will tell us the order in which we need to harvest those things. We could be fancy, we could try and sort it, we could try and find a really efficient path through, but we're not going to do that. We're just going to iterate through our sunflower petals, and here's where I'm going to check the documentation and see what sort of iterate. Okay, we have 4 numbering lists, that's nice. Do we have like reversed? That would be so nice, wouldn't it, if we did? Let's see, print reversed 1, 2, 3. Reversed has never been defined. We can iterate, we could implement reversed ourselves, but it'd actually be easier just to insert them into the sunflower petals in the order that we actually intend to iterate them. So that means instead of here passing in this position petals minus min, it's going to be max minus this position petals. So for 15 we're going to go into the 0th index, and for 7 we're going to go into the 8th index. So 0 to 7. Does that sound right? Okay. Yeah. So now we can iterate through this. So for cells with same number of this is a really long name. Cells with same number of petals in our sunflower petals 2D list. This is now going to be a 1D list, which is all of the cells that we need to harvest. So for cell to harvest in this really long name, we want to move to that cell, move to cell to harvest, and then harvest it. So let's see what this does for us. Don't think we need the prints anymore. It is occurring to me that as this process goes on, we're going to have fewer sunflowers. So it's not like we actually get 216. We probably get just over half of that. But anyway, let's see how much power we get from one traversal like this. So move to origin is not defined anymore. Okay. Move to 0, 0. Max. What was the problem there? Error. The index 8 you tried to access was outside the list. Okay, so 7 goes into index 8. Okay, so this needs to be +1. Off by 1. Errors abound. I nearly paused at that point as well before. It just felt wrong. Now. Beautiful. Okay, 135. That's a fair amount of power. We need to decide how often we're going to be planting sunflowers, but let's have a look how long this is going to last us. So 135 power. We did 1 full traversal. Oh, it's going to last ages. Nice. Oh, this is beautiful. Right, now we need to decide when to do all this stuff. So let's stop this for a second and think about it. Obviously, we're traversing. You know, it'd be nice to build this into our traverse function. I wonder if we have access to globals in this. Do we get globals? In Python, it's also, yes, to declare that you want to use the global variable instead, but this is not supported. Okay, so we can't have globals. We could still do state within a cell function. And now we know about default arguments, like move to. There's kind of a neat way of doing that. Yeah, let's try building some state into our cell functions, because I'd really like to refactor this to use traverse farm. So let's have a look then. So traverse farm, cell function. The way that this is going to work is we're going to add this state idea. So we'll have an initial state, which is going to be none. So all of our current uses of traverse farm are going to be passing none in here by default. So they're all still going to work. And we need to make sure that we still call cell function appropriately if initial state is none. But for our new fancy cell functions, they're going to take in the state and then potentially mutate it and then update the state. And then finally we'll return that value from here. So I'll implement it and then we'll talk about how it actually works. So let's get our position tuple. And it makes sense at this point to refactor the cell function to take in the position tuple rather than the X and Y coordinates separately since we've already got our get pos stuff. So currently I've just extracted get pos. Let's make sure all our calls still work. So we're calling traverse farm with plant in cell and with handle cell. So handle cell wants the position tuple now, which we'll just call position. You know, it's 2024. So handle cell takes a position and then plant in cell takes a position. So this needs to take a position, and then entity to plant takes a position. And then this is where we need to unpack it. So position 0 plus position 1. So all of this should still work. Let's just run it and make sure that it does. Seems like it's working to me. And now we need to decide if state exists. So let's create our state right out here. So state is equal to initial state. If initial state, I could imagine a cell function in the future going via none, and that'd be reasonable. So if initial state is not none, then we're going to pass in, we're going to call cell function with the position tuple, and then also the state. And then we're going to update the state with whatever the cell function returns. So this is how we're going to keep track of variables that the cell function might care about. Otherwise, we just do the old stuff. And then finally, we return the state, which is going to just return none for the old stuff. So yeah, let's verify again that the old stuff still works. Seems to be working just fine. So let's talk about how we'd use our new traverse farm function with this. Our cell function is the stuff that lives inside here, right? So let's start extracting that. So this is going to be count sunflower petals, let's say. And we'll have a position here, and then let's just add a question mark for what does the state want to look like. We're going to measure this position's petals. In fact, we could inline this even, right? So if it's a sunflower, then sunflower petals append get pos. And in fact, instead of it being get pos, we're being told the position because we're a cell function now. So sunflower petals is our state. And we're gonna take in some sunflower petals, we're gonna mutate it, and then we're gonna return that as the state. So return sunflower petals. So now we need the initial state, and then we can get the final state out as the return value from traverse farm. I think we've kind of got all of the pieces that we need here. So let's do sunflower petals equals traverse farm with the count sunflower petals function. And it needs an initial state, which is the exact same initial state that we had before. So just like this, hopefully. So yeah, so traverse farm, we're now using this cell function, which is count sunflower petals, which works just like the other cell functions from before, except it takes in this state. And we start with this initial state, and then we mutate it and then return it back. It's a little untidy that this mutates the argument rather than creates a copy, but that's a discussion for another day. So let's see what sunflower petals looks like after we use this new method with traverse farm. I'm going to comment this out because we don't want to do it for now. For now, yeah, we want to plant a bunch of entities. Plant a bunch of sunflowers. Planted a full load of sunflowers. Does all this work with our new traverse farm stuff? It seems like it just works perfectly. Okay, so it's a little complex, I'm not going to lie to you. But this is a super powerful pattern. Instead of using global variables that we're going to mutate, we use this stateful iterator. So we've managed to extract only the new stuff that we care about for sunflowers. Like the fundamental thing that we're doing is iterating around the farm, which we already have a function for, so let's keep using that. And then the new stuff that we're doing is just keeping track of the number of sunflower petals in this new list. And we can do that within the old paradigm just by extending the traverse farm function without changing any of our existing code. So that's a super neat and elegant solution. So let's start tidying this up. Let's start building it into the actual production system. Create 2D list is definitely a utility. And I think we want a new code block for constants, because constants are something that we're probably going to want to have more of. Let's decide that we're going to plant sunflowers if we have less than 50 power. And let's see where that gets us. In fact, that's a perfect use case for a constant, right? Minimum power. let's say, or let's say power threshold to plant, no, minimum power. Minimum power of 50. And if we don't like it, we can tweak it. If num items power is less than the minimum power, then traverse farm sunflower stuff. Otherwise, we do the old stuff. Okay, so sunflower stuff. We're potentially in a weird state at this point. You know, we need to harvest whatever's already there, and then we need to plant. So let's extend our planting cell function to have an entity, which is going to be none by default. And if the entity is none, then we go and find it using our prioritization algorithm. Otherwise, we're just going to plant the entity that we pass in. Our sunflower stuff is going to be def plant sunflower position. It's exactly like this, right? Basically. If you can harvest or there's nothing underneath you, harvest. Or maybe we just plant over it. You know, we're not going to lose much, I don't think, at this point. So if we can harvest, then we harvest. So it's not quite the same. If we can harvest, then we harvest, otherwise we just plant over it. So we plant in the cell the position, and we plant a sunflower at that position. The idea is in the long run that we do this infrequently relative to the other stuff. Maybe sunflowers is its own thing, maybe this is just sunflowers. So let's call this def. In fact, all of the new stuff can go in here, can't it? Def plant and harvest sunflowers. So we do the, so plant sunflower can go up top because that's the first thing that we're going to do. Not that it matters, I just like to organize things like that. And then instead of here, this is the function that we're going to call. So instead of calling traverse farm down here, we call plant and harvest sunflowers from main. So the first thing we do is traverse the farm and plant the sunflowers. Then the next thing we do is we traverse the farm and count the sunflower petals. And then the last thing we do is we go and harvest them all. And I think this can go in a new line here just to give us a little space. And the idea is if we've not got enough power, then we're going to plant and harvest sunflowers. Otherwise we do all our old stuff. So let's see what happens here. So here, error, minimum power has never been defined. Do I need to run this then maybe? If I run this. So constants, maybe constants don't work. Okay, well this is something that dicts could be useful for. We don't have them yet. We can have, let's put our constants in the appropriate boxes for now. Eventually we could have a function that's like get constants, and that's going to return these specific constants. But this should work for us. So we traverse here, we're low on power, so we plant a full lot of sunflowers. And then, why didn't that work, by the way? Am I missing something really obvious? Like, oh, the global scope is the scope of the outer box that you run, not the scope of the cell where it's defined. Okay, so that's fine. So all our constants go at the top of main. Cool. Good to know. So we are going to go ahead and plant everything. And then we go and measure them all. And then we harvest them, but they've not finished growing yet. So that's not good enough. That is not good enough. We need to move to the cell, and then while not can harvest, I think you just do nothing, just like continue. Because I think while takes time and doing a flip takes longer, so I think this works. For now, let's make our minimum power 100. This should go ahead and, okay, yeah, we still have our old traverse farm. Do we need that anymore? Question, not sure. But anyway, we planted a bunch of sunflowers, we go and measure them, we wait for that one. Wait. Right, okay, this is looking great. So now we're harvesting a ton of power, and then we're going to go back to planting pumpkins. Now we're back to even with everything. We're planting all sorts of stuff. And our power's going down really slowly. and we're not wasting too much time. Things are growing. I'm really pleased with that. The power seems to be a worthwhile diversion. Yeah, it'd be nice to keep track of what we expect to see next so that we don't end up with these long runs of things, but that is more efficient for pumpkins. We're doing really well, so our power's just dropped below 100, so now we've started planting a bunch of... but we're not... it's really cool seeing it jump around to exactly the right one. That's so awesome, dude. It's weird that we didn't plant over the carrot, isn't it? Oh, yeah, okay, so if can harvest, so I guess they weren't quite fully grown at the time. We didn't harvest them, but we didn't plant over. So we actually just want to harvest regardless. Yeah, okay. So that should work for us this time. This time we got rid of all the carrots. I don't know if that's... Oh, it's so cool. Yeah, it's so cool just jumping to exactly the right ones. Oh, man. Yeah. We could continue optimizing this slightly, but I think the next thing to do is going to be to look at mazes, which I actually accidentally unlocked when I was looking at the unlocks earlier. So let's see what's in store for us with mazes. If you use fertilizer on a full-grown bush, it will grow into a maze of hedges with 10% probability. For some reason, the drone can't fly over the hedges. Nice, so we got some mazes to solve. I think that seems super cool, and that seems like a good goal for us next time. So if you enjoyed this and you want to make sure you don't miss the next episode, make sure you subscribe and hit the bell icon.